Howdy, I'm the amateur logician. We're going to complete section 6.2 based on the Suppes and Hill textbook. We'll be covering several arguments and proofs with 2 or more universal quantifiers. It's time for argumentation. Exercise 5b is from page 227 of the Suppes and Hill textbook. We're to translate the following arguments into logical symbols and give a derivation of the conclusion from the premises. Premise 1 tells us that everything in this lesson is part of logic. Is a universal affirmative proposition. We'll say T represents this lesson and L represents part of logic. Thus, for premise 1, we have for all x, if x is in this lesson, then x is part of logic. For all x, Tx arrow Lx. Premise 2, any person who can figure out any part of logic is a genius. We have this any person and this any part of logic. There are thus 2 quantified variables. We will say any person is y and any part is x. Furthermore, we have a relational predicate, figures out. We'll give F for figures out and G for genius. So 2 for all x, for all y, f, y, x, y can figure out x, and Lx, x is a part of logic, arrow, gy, so y is a genius. Third premise, Karen is a person who can figure out the first derivation, and it is in this lesson. We have that and, we have a conjunction. There is a 2-placed predicate. So for 3, we have f, k, lowercase f. Karen can figure out the first derivation. So little f, lowercase f is his first derivation, and tf. In other words, this lesson is the first derivation. Conclusion, therefore Karen is a genius. So therefore, GK. For line 4, we should do some universal instantiation of line 1. The question is, what should we substitute for x? And it's going to have to be this first derivation, right? So it will be lowercase f. So we'll say tf arrow lf by the universal instantiation from line 1. For 5, let's work on the second premise. We're going to instantiate f, but also k for Karen. So, because y is any person, we want to instantiate Karen specifically for that y. So we will get parentheses f, kf, and lf, close parentheses, arrow, gk, by the universal instantiation, line 2. Line 3 has tf. Let's get that by itself. So for line 6, we'll first do the commutative rule. We'll say tf and f, kf, commutative rule, line 3. And then for 7, we can get tf by the simplification of 6. For 8, we can do a modus ponens inference, because tf appears up here as the antecedent. So for 8, we'll get lf by modus ponens for 7. For line 9, we can get f, kf by the simplification from line 3. Now we can combine. For line 10, we can get f, KF and LF by the conjunction rule, lines 8 and 9. And now we can do another modus ponens inference because of line 5, or with line 5. So for 11, we can now get GK by modus ponens 5 and 10. So Karen is a genius does follow. Before we move on to argument number 2, I do want to point out that I made one implicit assumption, namely that Y is a person. I didn't include that when I translated the English sentences into the predicate logic. Probably most textbooks, because they're very, very fussy, and frankly for good reason, because they want us to be very precise, would mark us down for not including that fact. We're told, after all, in premise 2, that we're dealing with any person. And likewise, in premise 3, we're explicitly told that Karen is a person. How can we modify our symbolized argument to include that fact? Well, look at premise 2. Look at the antecedent here. We would just include in a conjunctive relationship that Y is a person. So we'll say PY and FYX and LX. This would be our new antecedent for premise 2, and likewise, we would have to modify premise 3 to include the fact that Karen is a person. So we'll say PK and FKF and TF. This will be our new premise 3. So now we've included the fact explicitly that Y is a person, that Karen is a person. The derivation obviously would basically be the same, but there would be a few additional lines because we have some more information. Oftentimes, translating is an art. It's not an exact science, so just be aware of that. But because most textbooks probably would want us to include the fact that Y is a person, we just modified our translation a little bit, and then we can go from there. All right. Argument number 2, we have mongooses can kill cobras. Can kill is a relation. We have two general terms, mongooses and cobras. They do not reference a specific unique individual. Rather, they are about general classes of things. Thus, we need two quantified variables. We'll write premise 1 for all x, for all y. Notice as well that we have a universal affirmative proposition. So we'll have a conditional here. In the antecedent, we will announce, so to speak, that x is a mongoose and y is a cobra. Parentheses, mx and cy, close parentheses, arrow. The consequent will have a relational predicate, kill. So k, x, y. X can kill y. In other words, a mongoose can kill a cobra. Second premise, we have Montgomery cannot kill Charlie. We have two specific individuals. We have a relational predicate, kill. We have a denial, cannot. Premise 2, it is not the case, KMC. It is not the case that Montgomery can kill Charlie. Therefore, if Charlie is a cobra, then Montgomery is not a mongoose. There's a conditional. The antecedent, we have CC. Consequent, we have not MM. Where uppercase C is cobra, lowercase c is Charlie, uppercase M is mongoose, lowercase m is Montgomery. For our derivation, we should instantiate line 1. The question is, what should we substitute for x? What should we substitute for y? Well, it would have to be M for x and C for y. M, Montgomery, C, Charlie. So we'll get parentheses, MM and CC, close parentheses, arrow, K, MC. By the universal instantiation of line 1, notice that line 2 we have not KMC, that denies the consequent on line 3. Hence for 4, we'll get not parentheses MM and CC, close parentheses, by modus tollens, lines 2 and 3. Let's work on line 4. We can get not MM or not CC by De Morgan, line 4. For 6, because we have a conditional, let's do a conditional proof. We'll assume CC, that's just an assumption, and because it's an assumption, we will place it under quarantine, so to speak. It'll be in a box. And then, because we're going to do a disjunctive syllogism eventually, let's double negate it. So we'll get not CC, double negation, 6. For 8, we can get not CC or not MM by the commutative rule, line 5. This not CC denies not CC. So for 9, we can get not MM by the disjunctive syllogism, lines 7 and 8. So our assumption is CC, and from that assumption, we're able to get not MM outside of quarantine. For line 10, we can say, therefore, if CC, then not MM by conditional proof, lines 6 through 9. Thus, if Charlie is a cobra, then Montgomery is not a mongoose. Argument number 3. Anyone who likes George will choose Nick for his team. Nick is not a friend of anyone who is a friend of Mike. Jay will choose no one but a friend of Ken for his team. Therefore, if Ken is a friend of Mike, then Jay does not like George. There's a lot of relational predicates. Actually, all the predicates are relational. The first premise, we have George and Nick as specific people. We have this anyone, all people. Hence, it's a universal affirmative proposition. It will be a conditional. Premise 1, for all x, LXG, arrow, CXN. If X likes George, then X will choose Nick. Premise 2, Nick is not a friend of anyone who is a friend of Mike. This is a universal negative proposition. Thus, the consequent will be negated. We also need another variable, such as y. So, for all y, f, ym, arrow, not fny. If y is a friend of Mike, then Nick is not a friend of y. Premise 3, Jay will choose no one but a friend of Ken for his team. It's really a universal affirmative proposition. Just says that Jay will choose a friend of Ken for his team. So for 3, we'll have for all z, c, j, z, arrow, f, zk. If J chooses Z, then Z is a friend of Ken. Conclusion. Therefore, if Ken is a friend of Mike, then J does not like George. So F, KM, arrow, is not the case, L, JG. If Ken is a friend of Mike, then J does not like George. A lot of universal instantiations are going to happen. There are 3 variables, x, y, and z, so we have to be careful what we substitute for what. Obviously, we want to end up at this conclusion. There's different ways to go about this in terms of your strategy. Obviously, you want to think ahead. What I'm going to do is first instantiate the first 3 lines in a very general sense, and then we can make corrections. So I'm just going to say for lines 4, 5, and 6, I'll just say L, XG, arrow, CXN, universal instantiation 1, FYM, arrow, not FNY, universal instantiation 2, CJZ, arrow, FZK, universal instantiation 3, and then we'll correct, so this will be 4, 5, 6. Okay, now what? Well, we do have a conditional as our conclusion, so we can do a conditional proof. So for 7, thinking ahead, we could say FKM. This is an assumption, and we'll place it under quarantine. And this gives us a hint in terms of what we should substitute for what. So for 7, we have this FKM, but notice that for 5, we have this FYM. So we really should substitute K for Y. So for line 5, we can get FKM, arrow. It is not the case that F and K, and this is the universal instantiation of line 2. Now let's notice that here we have this not F and K. This also gives us a clue. With line 6, we have this FZK. So let's substitute N for Z. So for line 6, we now have C, J, N, arrow, F, N, K. Universal instantiation 3. And now, here we have this CJN. On line 4, we have this CXN. Moreover, just by what we've done so far, we'll need a J there. So we'll get LJG, arrow, CJN, universal instantiation, line 1. Now we're good to go. For line 8, what can we get? Well, we made the assumption on line 7 of FKM, so we can do a modus ponens inference from line 5. So for 8, we can get not F and K, modus ponens, 5, 7, under quarantine because we have an assumption. Line 8 tells us not F and K, and this contradicts or denies this consequent on line 6. So for line 9, we can get it's not the case, CJN by modus tollens, lines 6 and 8. We're told not CJN, this contradicts line 4's consequent. So for 10, we can get not LJG by modus tollens for 9. And now, based on our assumption from line 7, on line 10, we got not LJG. So for line 11, we can say it is the case that therefore, if KM, then not LJG. So therefore, if Ken is a friend of Mike, then Jay does not like George. Now we have argument number 4. We're told that only a fool would feed a wild bear. Feed is a relational predicate. We also have 2 general terms, fool and wild bear. But because we have 2 general terms, we need 2 quantified variables. Moreover, we have a universal affirmative proposition, hence we'll have a conditional. The antecedent, so to speak, always will announce our variables x and y. Our consequent will end up at one of those variables being a fool, which we will just label S, or for stupid, and F will just lead for feed. So for premise 1, we'll say for all x, for all y, parentheses, bx and fyx. X is a bear and y feeds x, arrow, sy. Y is a fool. Premise 2, we have Christine fed Nicholas, but she is no fool. We have another relational predicate, namely feed. This but really indicates an and, so there's a conjunction there. So we'll say for line 2, which is a premise, we'll say F, Cn, and it's not the case that SC. So we have Christine fed Nicholas and Christine is not a fool. Conclusion, therefore, Nicholas is not a wild bear, so it's not the case Bn. For line 3, we'll do our instantiation of line 1. Nicholas will have to be X and Christine will have to be Y. So we'll say BN and FCN, arrow SC, universal instantiation, line 1. If Nicholas is a bear and Christine fed Nicholas, then Christine is a fool. Line 4. Let's deal with line 2, where eventually we can get this not SC. So we'll say not SC and FCN by the commutative rule, line 2. And then for 5, we can get not SC by itself by the simplification of 4. Not SC denies this consequent. So for line 6, we can say it is not the case, parentheses, BN and FCN by modus tollens, 3, 5. We can do De Morgan's rule, so we'll get not BN or not FCN by De Morgan, line 6. Notice in line 2 we have this FCN, which is contradictive to not FCN. So for line 8, we can get FCN by the simplification of 2. For 9, we can double negate that, not FCN, double negation 8. For 10, we could say not FCN or not BN by the commutative rule, line 7. And then for 11, we can say not BN by the disjunctive syllogism, 9 and 10. And so we have reached our conclusion. It does follow that Nicholas is not a wild bear. Let's look at exercise 5C. I'll do 2 problems here, number 3 and number 10. Number 3 asks us to prove that 3/4 is less than 1. Well, obviously 3/4 is less than 1. Really the question is, can we prove this just given these 2 premises? It's kind of interesting that we can do that. Just consider all the basic proofs in high school geometry, in Euclidean geometry. It's really interesting how various statements can be used to prove other statements. At any rate, we're told that 4 is indeed greater than 3, and that is really what we should substitute in terms of the W and the Z. For line 3, we can say W is 4 and Z is 3, and 4 is greater than 3. Arrow 3/4 is less than 1 by the universal instantiation of line 1. We're given that 4 is greater than 3, so for 4, we can get this consequent by modus ponens. So 3/4 is less than 1 by modus ponens with lines 2 and 3. So that's really simple. Number 10 is a little bit more interesting. We want to prove P7. We're given 3 premises. We're told, for example, that 7 is in fact greater than 0. For line 1, we have for all x, for all y, x is greater than 0, and y is less than 0, implies nx over y. For line 2, we have for all u, for all v, u is less than 0, implies nv over u, implies nv. For line 4, we're going to work on premise 1. Well, 7 is greater than 0, so let's substitute 7 for x. What about y? I think we should just leave that alone. So we'll get 7 is greater than 0, and y is less than 0, implies, we can put parentheses here. Some textbooks require that, the Suppes and Hill textbook does not. And then we have n 7 over y by the universal instantiation, line 1. What about instantiating line 2? What should we substitute for u? Well, here we have this u is less than 0, and this is very similar to y is less than 0. So why not substitute y in for u? Then the question is, what do we want to substitute for v? So v shows up here with p, so definitely we're going to have to substitute the number 7. So for line 5, we'll get parentheses, y is less than 0, arrow, n7 over y, close parentheses, arrow, p7, but the universal instantiation, line 2. We want to prove this p7. How are we going to get that? Why don't we make an assumption that y is less than 0? Because if we make that assumption, we can then put it in a conjunctive relationship with the fact that 7 is greater than 0. So we would have the means to derive by modus ponens n7 over y, and that will allow us eventually to get our conclusion that's desired. Hence, for line 6, we'll say y is less than 0, and this is just an assumption. We'll place it under quarantine, so to speak. Then for 7, we will combine that with 7 is greater than 0. So we'll say 7 is greater than 0, and y is less than 0. This is the conjunction of 4 and 6. And now we have this antecedent, if you think about line 4. So for line 8, we can get n7 over y by modus ponens 4, 7. With this assumption, line 6, we're able to get this result. So outside of quarantine for line 9, we can say if y is less than 0, then n7 over y by our conditional proof with line 6 through 8. And this here shows up as the antecedent to line 5. So for 10, it therefore follows P7 by modus ponens 5 and 9. Pretty good. And that concludes this video. Up next is a so-called bonus video on relational logic. We'll deal with not only universal quantifiers, but also existential quantifiers. I'll see you then.